Today in this mini conference will be a Blackboard talk. That is my preferred medium, but the previous talk can be excused because it was very, very hard to draw the Blackboard by Professor Shaoshi, Chen from the Chinese Academy. We'll speak about structure of rational WZ class.
Thanks.
And let me know after the talk whether you can join us for dinner. Let's do this.
Thanks for Dora inviting me to give talk. This is my third time to give talk here. So previous time I both used the slides. This time I prefer to use Blackboard, maybe to be explaining something in a slow way. And usually I was complained by the audience, also my students, I speak too fast. And but anyway, and I would like to dedicate my talk to in memory to my hero John Bowen, and he's the master of this experimental math. This is also the name of this seminar. So I will talk about the rational doublet pairs. First, let me give a definition. What is doublet pair? So the doublet pair actually is kind of function, which is a pair of function f, y in two variables, and they satisfy the following so-called doublet equations. That's depend on the different type. I will talk about different type of the equation. This is the equation usually people call the doublet equation. And here the partial x can be different depend on the problem. So it can be a derivation with respect to x or y, d, or some shift or difference operator with respect to x, or q difference operator with something, with the variable. So this actually depends on the choice of so partial x or partial y up to the symmetry. There are 6 types of the different type doublet equation, and also correspond to different 6 types of the doublet pairs. So as a mathematician, usually all the research starts from solving equations. So this is the main equation in our talk. I will focus on this innocent equation. Seems very easy equation, but actually this is the one equation with 2 unknown functions. I never talk about very special solution because otherwise it doesn't make sense to solve this equation. So today I will focus on the rational solutions, how you can find all possible rational solutions of these simple equations. And definitely before I going to solve this equation, let me motivate why we care about this kind of doublet equation. Let me show you some examples. So why do you care? The first motivation for this, because this is very useful for proving identities. Identities. Let me take a very simple example. This is the very classical identity. I will show you how you can use this pair to prove this identity. Definitely, Dora can give a very brief introduction to this method, but nevertheless I will use this example. So, how you can prove this identity? The idea is you can, because here is in closed form, and then you move this on this side, you get the equivalent identity, which looks like this. And that is, you want to prove that this actually is a constant, which is 1. And then the idea is you want to prove that actually this is the free of the, this is the, you can interpret this as a sequence of n, and you want to prove that actually this is just a constant. And how you can prove something is a constant? You want to prove that actually this is the difference of this side is equal to 0. That's the idea. And then this, let me denote this f is the summand. This is just for notation. So now the idea is actually for this f, you can compute another companion, which is a g, and g has the following form. This is all can be done by computer algebra system. They call the using the Gosper'algorithm. Just write down this carefully. I do this by maple, so I don't need to really do the calculation by myself. I need so this is a kind of g actually is a polynomial in n and k times this summand f. You simplify a little bit. You can simplify this a little bit. So you can simplify it just to remove those two factors. And so now you can see from this identity, you motivate to get this kind of a pair. Fg, they satisfy this equation in the purely discrete setting. And then how you can prove these identities? You will sum over this. You want to prove that actually this is the sum, or you sum over this with you sum for n from for k from 0 to n on both sides, and then you will get delta n f. And then notice that you can commute those delta n and the sum n with respect to k, but it's not the fully. You can commute. You can change this the order of this. So this is the left hand side of the identity. But then that's not equal. Actually, there are some you need to adjust this little bit because this is not commuted totally. So you will need this thing m plus 1. So this is the left hand side. So you get this. This is the form you want to prove. And then on this side, when you sum with respect to k, you get already telescoping sum. So this side is easy to evaluate. Actually, you use the discrete Newton-Raphson rule. You can evaluate this easily. So I will just write down the result. So this is actually equal to t n m plus 1 minus t n 0. And this is equal to 1 minus 2m plus 2 n plus 1. And then you because this is equal to this one. So what do you get? You can cancel out this one, and then you get delta n. This is the left hand side of the identities. You see, I just do the. What this means? This is 0, which means this is free of the parameter n. This is a constant. Then you to verify to compute the constant, you only need to take one. One value, take n equal to 1, then you get this is 1. So you prove that actually.
You can make it simpler, n equals 0.
What?
Why not take n equals 0?
Yeah, sure, definitely. Yeah, definitely you can take n equal to 0, you get 1 easily.
N equals
so
1
then,
is you have to do 1 plus 1.
Yeah.
1 plus 0.
Right. So that's then you can take any fixed value, you get then you can fix the constant, then you prove the identity. So that's you see. The pair, this double pair, play a very significant role in this proof. So once you get this compare, and this is by computation, then after that is very routine verification, then you prove the identities.
Yeah.
So you see,
for n equals 0, it's trivial. But for n equals 1, it's a deep 0.
Right.
1 plus 1 over 2 equals 1. Another 1 plus 1 equals 2.
Yeah, indeed. So, yes. And then you see, what I did is I sum over this equation with respect to k, but you can also sum over with respect to n. Then you actually, by summing over with respect to n, you get a new identity, which I just write down. I will not prove this identity, which is the following. If you sum over this pair, not with respect to k, but with respect to n, you get the little bit complicated, but still nice. I mean, I will not go through all details. You see, it's funny that actually this kind of doubly pair, a pair leads to a pair of identities, in fact. So that's a nice thing. So once you have this kind of a pair, you can get a pair of identities. That's the nice thing. So usually, how people can find those kind of F and G, the idea usually is motivated by identities. Then now the question is, you can inverse this kind of thing. How about if we can solve this equation, write down all possible F and G, and then we can get the infinite many of identity. That's kind of motivation of my work. Yes, you can start from some combinatorial identity. Then you can find such kind of FG. Then let's inverse this idea. Let's inverse the procedure. Now we only focus on this kind of equation. We try to solve without any inspiration from the combinatorial identities or books or something volume of mathematical handbooks. Let's just focus on the example, focus on this equation. How we can solve for certain special class of solutions. That's the goal of my talk. Maybe the second application of this double pair, I just briefly mention. This is used for but that's also in Dolan's so-called convergence. convergence-acceleration, which is used for studying some, this zeta 3 value. The idea of using this kind of double pair to study the convergence acceleration actually can went back to very long, somehow Markov, somehow like this. In your paper, I see this 98 yellow. And there's a nice paper by Doran named the closed form pun, forget the pun unintended. So this is the Doran's paper in 1993. There's a paper by called closed form pun intended. So in this paper, they give a nice introduction to how you can use double pair to do the convergence acceleration. And the basic idea in this, this is using this Doran's one of the main theorems, which is due to Doran's. And the idea is, once you have a pair, then you can automatically get another identity, which is the following form. N equal to 1, and to the infinity, and f, n minus 1, plus t, n minus 1, n minus 1. And this is equal to, this is the nice part, n equal to 0 is t, n, 0. Notice that after this is a constant, no longer a sequence, right? This is a constant. Then, if you take this pair, like for example, if you take the pair like f equal to minus k, right? Next time, but magic will come later. So this is a very complicated formula. But actually, they are the pair, so they satisfy the double. Yeah, time to write down, but anyway, I will. So this is a pair which is, you don't care about how we can construct, but you can verify that it satisfies this kind of double equation. And then using this theorem, you will lead to the following nice formula for the zeta 3. N from 1 to infinite. Let me remember what the zeta 3. This is the definition of the zeta plate. And this is by using this, actually you sum. Actually, this side is just this one. This is equal to this side, and then you get evaluate this. You will get the following formula. So this is converged very slowly because in each time you only get a polynomial thing. But then after using this double pair, what you get is 2n to the n square, which is means if you do add, you will get a very fast convergence because that's very big. When n is big, this is very large. So you see, but they are equal, so you can use this one to compute the zeta 3. That's the way you can accelerate the convergence. So that's the two main application of double pair. Now I think we are enough motivated why we care about this double equation. So now let me really turn to the solve this equation for rational solutions. I know that actually this is my kind of ambitious goal to solve this equation for like hypergeometric solution, but I started this kind of project not long ago. So I only, for the moment, I can only solve this rational case. So, but I think that I will show you actually rational case is already very interesting. Okay, so there's one book by Riordan on the combinatorial identities. And let me recite one sentence from his preface of the book. It says that the central fact, so developed, is that identities can both be exhaustively and unpredictable. So I mean identity is unpredictable. And there's one sentence says, age-old gene of putting order in this chaos is doomed to failure, which means you cannot put order to list of common identities. this is a kind of things, no hope to get what is the classification of the combinatorial identities. And then there's in 2011 there's a workshop dedicated to in honor of Wilf's 18th birthday, and Ila Gesell gave a talk and about WZ methods, and he make a very optimistic comment, say that WZ pair or WZ form bring order to this chaos. So that's he make very strong comments on this. So I was thinking about how we can really bring order to these combinatorial identities. I think the first step is we should understand this WZ equation in a more precise way, which means how we can solve this for certain special solutions. Now let me turn to the solving this equation. Now from this moment on, we will only focus on f is rational functions. Let me talk about how we can find all possible rational solutions of this equation. The first, let me rephrase that. Actually, when you look at the set of all solutions, actually this is a form of a linear space. It's from a linear space because easily you can check that this is a, so C x, y, this is a rational function field. This is a vector space over C of dimension, infinite dimension. But then you can focus on this all pair of this. They satisfy this equation. So because partial x and partial y is linear, so also is linear with respect to over the C, and then you can easily check that the set of all possible W pair form a vector space over C. That's easily linear algebra exercise. But then the question is, you know that all vector space has basis. Now you want to describe the all possible pair, you need to describe the basis of this vector space, or generating set of this vector space. Okay, now the following I will describe the basis of this vector space. And before I doing this, let me write down some trivial, I call it trivial or we call it exact pair, which is you can easily cook I call the exact pair. You can easily find some solution of this equation, which is you can just take f is equal to, this is equal to, because in our setting the partial x commutes with partial y, so you can take one easy solution of this is you just take any rational function, you apply partial y to h, and you take h and then apply partial x to h. And then you can easily see that because partial x partial y commutes in this field, and then this is definitely the solution of this. But this is not interesting because this is that's why I call exact. Actually, exact has some meaning for this equation. This is motivated from the differential form. So if I have time, I can say more about it, why we call this exact. Anyway, that's kind of a trivial pair. You can easily get this solution. So now the natural, also you can check that all those kind of exact pair, they also form a subspace of this vector space. And then you need to understand the quotient space of this. And then that's the next goal. Now we need to do some case distinguish, because I need to pick out different type of these pairs. So the first natural case is both partial x and partial y are derivatives with derivation with respect to x or y. So I call this the differential case. Differential case, partial x actually is the partial derivation with respect to x, and partial y is the partial derivation with respect to y. And then that's I already say that the exact pair. I just try to repeat this in order to. So you can. So exact pair will be. You can just take this partial y a and g is partial x a for any a in c x y. So this is the exact pair in this case. And then now we can write down another. Maybe you can already guess that you can look at this equation, and you can figure out actually there's another kind of little bit non-trivial pair, which is I call the derivative, log derivative pair. So what's this? Actually, I can write down this. So this is log derivative pair. What's this? F. You can take any rational function b. So you just think about this. Sorry, let me. Yes. Now it's the derivative. So you can take this called the partial y and b over b, and g equal to partial x b is equal to b. So this is also satisfied this double equation, because what this comes from, actually you can think about f is something like log the derivative with respect to y of log b. Right? This is if you take log b, then you get this, and then g is the partial x of log b. And then now you go out of the rational function field, but still get this motivated this y. You can easily see that it's something like the exact same, but now you use this log b. But by taking log b, you go out of the rational function field. That's not good. But anyway, you can use this to verify, to motivate the y. This easily satisfies the double equations. Well, but this also comes from the commutativity between the partial x and partial y in the rational function field. And then we see that that's the two pair which is you can figure out. Now the question is that whether that's all. Actually, now this comes the theorem. So the theorem is about that's all. That's all possible thing you can get. So this is the theorem. Actually, this is not my theorem. This is due to Christopher. The people who studied the polynomial vector field, and they turned out they needed to understand this kind of structure thing. It's 1999. And then this is for the bivariable case. Actually, there's also a multivariate version which due to the dollar deck. It's people working on differential equations. And then actually, Christopher and I actually recently proved a conjecture on this, what we call the double conjecture. And in our paper, actually, we also reprove this material version of this result. And let me write the result. If fg are rational function, so if they satisfy this double equation, we find only, so then you will find a rational function a, and b1 to bn, and also some constants in C such that f and g are the following form. This is the So basically, in formal way, the theorem just shows that actually any doublet pair can be written as a linear combination of exact and log derivative pair. That's the.
Do you have an algorithm to find?
Sure. Yeah. But you can, this is any. You just choose A and B, then you form this all possible doublet pairs. So you can get all.
But if you have input F and G, so you can easily make up the things.
Yes.
But if it's hard to.
Oh yeah, given F and G, you can first verify this equation and then you can decompose in this way. There's algorithm to do this decomposition, find A and Bi's.
So it's a fast algorithm?
For the moment, there's one. We have one algorithm, but I don't know whether I think there's no comparison faster or not because somehow
there's only one.
Only one. That's what I understand. Okay. So that's the differential case. Then I will go to the next.
But is it a polynomial time algorithm in the size of the input?
No, I think depends. So because maybe n can be very big. It depends on the f and g. So maybe you can. You can also easily cook up some very nasty example to make the algorithm very costly, time-consuming somehow. Okay, now the idea you can see that this vector space actually now we find in the differential case we find all possible identities, not basis but actually generating sets for the vector space. Anything is a linear combination of those typical pairs. And now let's turn to the shift case. which we show the similar result. So in the shift case, we will have different cases. So in shift now, this is the difference operator with respect to x, or shift, Q shift different. So now actually there are several cases. That means partial x can be shift operator with respect to x, or Q difference operator with respect to x. And partial y can be also the same. And maybe I need to remind you what's this for that. Many people already know. It's just the usual difference operator. And the Q case will be, we do the Q shift. So that's just Q. And Q, suppose Q is not a root of unity. And not another integer. That's just a Q shift thing. And in this case, you also start from some easy things with exact pair, the same. That's why done. F can be shift case, that can be a shift of some rational function and x, and any rational function. Or here also can be Q shift, but anyway, that's the trivial one. For anything, you can also write down this exact thing. Now, in this another case, except this exact pair, we introduce so-called cyclic pair. This is a little bit can be viewed as a shift analog of log derivative pair, but somehow it's a little bit complicated. So let me explain this. So before this, I need introduce some notation. So actually, on this field, we can focus on two automorphisms, which is just one by one morphism, and then like sigma shift with x, shift with y. You can take this, but then we can take any automorphism, and so they are commute with each other. Then I can introduce the following notion, which is can take y equal to sigma n over 1. You can apply to h. So this is just a notation, because that makes sense that you take quotient of two operators, because what's the meaning of 1 over this operator? But then this is just a formal notation. So this is when, because this is always divided by this. So when n is positive, then you know this is equal to usual thing. Just apply this sigma x to g to h, and n greater than 0. When n is negative, now it's different. Negative, then it gets. This is just a notation. So. Because I don't want to write down some formula which on the final theorem. This is just to use this notion, which I don't need to say n is a positive or negative. This formula works for all integers. That's just a notation. Then after that, then we can write down the nice. I'm not used to use big platform. I use in China. We only have a. Here I keep something here.